Well, good morning, good afternoon, and good evening. I am the Crazy Hat Chemist, of course, and we are going to continue on with our video here on periodic trends. Here we go. All right, so here we go. This is going to be part 2 of our, I don't know, multiple part series of periodic trends, and I got a couple new weights here to the Crazy Hat Chemist. So I have, we're going to start. We have done problems 1 through 11 thus far on our periodic trends worksheet. And we're going to start with number 12. All right. So we need another periodic table so that we can continue on with this little journey here. And then we're going to scroll this on up here and figure out what is the question for number 12. All right, so the question for number 12 is locate on the periodic table alkali metals, alkaline earth metals, transition metals, representative elements, intertransition elements, lanthanides, actinides, noble gases, and the halogens. So let's see if we can answer those questions. Of course, we're going to label this on a periodic table, and that is how we do this. All right, so let's pull out our wonderful periodic table here. And we're going to have to zoom on out just a little bit so we get the full periodic table. All right, fantastic. All right, good. Put on my new weights. Here we go. Zoom on in just a little bit here. All right, so fantastic. So we're going to label all the parts on the periodic table. So the alkali metals, we will start with that. Okay, the alkali metals are known as group 1. So let's see here. Let's see if we can write this down here. Alkali metals, that equals group 1. And that is this group right here. Okay, excluding hydrogen, that is, of course, right? Because hydrogen is not a metal, so it is not an alkali metal. If it's not a metal, it's not even an alkali metal. All right, so that's our first grouping here. And then we're going to do the alkaline earth metals. And the alkaline earth metals are group number 2. So okay, fantastic. So group number 2 are the alkaline earth metals, okay? And just a real quick little bit of trivia here that you should probably know. And the word alkali or alkaline means a base. And so that means if you were to place any one of these metals, that is lithium, sodium, potassium, rubidium, cesium, or francium, beryllium, magnesium, calcium, strontium, barium, or radium, in water, then what is produced? What is produced is hydroxide ions in solution. Not only is hydrogen gas produced, but hydroxide ions are produced, and hydroxide ions, that is an alkali metal. So that's why they are called the alkali metals or the alkaline earth metals, because they do produce a basic solution. All right, so our next grouping here are the transition metals. So that would be, so if you do remember or if you have done this already or not, we'll find out. Okay, but if you do know the S, the P, the D, the F type orbitals, it is the D block of orbitals are the transition metals. So right here in this segment here, this D block, these are the transition. Or transition elements, transition metals, they are the D block, if you remember the D block. So that's something to remember, certainly. All right, now we're going to come back to the representative elements. We're going to do the intertransition elements, and the intertransition elements are going to be right here. So if you notice that there is let me do this in a highlighter so you can clearly see this. there is element 57 and then 72. Notice that there's a gap right there. And then there's 89 and 104. So there are two gaps right there. So that first gap is right here with this orange line right here. And what belongs right there is this first F block. And then with the second one, this second one with the green line, there's a gap there between 89 and 104, and that block is right here. Okay. So hopefully you got that. So this entire grouping right here down below, okay, these are the inner transition elements. Okay, otherwise known as the intertransition metals, intertransition elements. It really doesn't matter one or the other. Okay, and then we have the element lanthanide. That's right here. And that's why these are called the lanthanide series, because they belong between the 57, which is lanthanide, and 72. In between there, that's 58 through 71. That is the lanthanide series. Okay, so that's written down right here on my periodic table. I don't know if it's written on yours. And then we have the element actinide, and the actinides are the actinide series. So that is between 89 and 104. So that's 90 through 103. Those are the actinide series. Okay. All right. So we got the lanthanides, we got the actinides. Now we're going to do the noble gases. Okay, the noble gases, I'm going to flip this off to the side so I can do this here. Okay, the noble gases are on the far right-hand side of our periodic table. These are the noble gases right there. Okay, and then we have the halogens. These are the halogens. It's most commonly viewed as the fluorine, chlorine, bromine, iodine, but this At would also be one, and this element here. We actually have elements here already. They're already named and numbered, but not on my periodic table. So everything in that column follows that same principle. All right, I'm going to do a couple other things that are not on this sheet of paper here, but that you should probably know. And this is uranium right here, element number 92. And anything after uranium for atomic number, that is 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, and that continues 104 all the way to 118. All those are transuranium elements. And for the most part, most people view the transuranium elements as man-made elements. That is, they were made in a cyclotron somewhere in a laboratory. All right, now we're going to do the representative elements. Okay, so the representative elements are elements that represent all the different characteristics of the elements generically. So here's what we're going to do. This is a folding activity. So I'm going to do one other thing here so that you remember this from hopefully the past. And if you don't, you'll have to relook at some of those videos. Okay, so this is the S block of elements right here in groups 1 and group 2. This is the P group right over here. This is the D group, and this is the F group. Okay, and these are types of orbitals. So if you don't remember that, then you should probably go look that up again here. Watch another one of my videos. And this is the S type, the P type orbitals, D type, and F type orbitals. Okay, so here's my fun way of memorizing the representative elements. So I'll have to write this down in just a little bit here. So the representative elements, what we are going to have in the representative elements, we're going to have metals, non-metals. We're going to have gases, solids, and liquids. We're going to have all the different generic types of chemistry without the extra flavor. Okay, and so here's how you remember this, and that is, what grade do you not want to get in your chemistry class? Well, that's an F. So what I need to do is get rid of all the F grades. So what I'm going to effectively do is fold out the F block of types of orbitals. So there's all my F's. I folded them out. So there we go. So now I'm left with S, P, and D type orbitals. Okay, and the other grade that you don't want to get, because many colleges don't accept that as a true passing grade, are the Ds. You don't want to get a D either. So what we're going to have to do is fold out the Ds. So first I'm going to fold into it, so it's facing me at the D block, just like that. So now I have the Ds, and the S's and the P's are off on the side there like that. Do you see that? So now what we're going to do is we're going to flip this down, okay? And we're going to place our hand right here and squeeze upon this. And then what we should have are only the S and P type orbitals, okay? And you should see that right there like that. Now we definitely need our weights, okay? These are the satisfactory passing grades in chemistry, which of course, this entire grouping right here, so this entire grouping of all this are called the representative elements. Now, I can't call them the representative metals or the representative non-metals or the representative gases or anything like that, but they are the representative elements. They are most certainly elements, and they represent the vast majority of elements on the periodic table. And so if you want extra spice in your life, then of course you're going to fold this out and include the transition, the D block. And if you want a little bit more spice in your life, then you do need to include the F block. All right, so that covers what we have for the alkaline metals, which is group 1, excluding hydrogen, the alkaline earth metals, which is group 2, okay, and then the transition elements, transition metals, because they're all metals, that's the D block. And the P block right over here, okay, within the P block, we have the noble gases, we have the halogens, okay, and in the inner transition elements, which are all inner transition metals, truly, those are the F block. And within this F block, you have the lanthanide series and the actinide series. Remember that the lanthanides fit between lanthanum and hafnium, and the actinide series fit between actinium and rutherfordium right there. Okay, so hopefully that works out well for you. All right, so now we're going to put this off to the side, and we're going to grab ourselves our worksheet here and come back to the problems within the worksheet. All right, so here we go. And so here is our next question. Our next question is number 13. It says, which element in each pair has the larger radius? That is the atomic size based on the periodic trends. All right, folks, let's try that again here. Number 13, actually my favorite lucky number, of course, right? I mean, wouldn't think that number 13 isn't the best number in the world. So which element in each pair has the larger radius, atomic size, that is, based on the periodic trends? And so again, what we need to do is flip over to a periodic table, and then we'll come back to this question here such that we can answer it. Okay, so need to zoom on out, and for the most part, we're going to be dealing with this grouping right here, and that would be the S, the P, the Ds. The S do apply to this as well, but we're not going to be worried about that as much. Okay, all right, so let's see if we can nail this one down here. Okay, so basic trends on size. So size trends, this is size. Atomic radius. Okay, atomic radius and size are the same thing. And that is the average distance away from the nucleus. And here are what's happening. And so what is the size as you go down a group? The size increases as you go down a group. So that's larger. Okay. And what happens as you go across a period? So as you go across a period, the size trend is smaller. Okay. But what I like to tell my students is, well, it's easier to remember two things that go together. And so that is, so you notice that as you go across the period, within any period, as you go from left to right, the size decreases. That's because the effective nuclear charge increases and the number of electrons within a different type of orbital has not increased. So that means that the size actually increases as you go to the left. So I'm just trying to get students to remember a particular trend. The correct trend for all textbooks, so just make sure that you note this, is the following. As you go down within a group, they get larger, okay? And as you go to the right within a period, they get smaller. However, what I'm doing is I'm saying, well, if it gets smaller within a period going from left to right, then you can just flip that arrow around and use that as it gets larger going from the right to the left. And then that will work as well. So what are we trying to compare here for our first set? So the first set is either sodium or lithium. So sodium or lithium. And which of these two has the larger radius? Okay. So which of these two has the larger radius? As you go down, the size gets larger. So of course, sodium would be the larger one. Okay. And then the next one is strontium or magnesium. So I'll do that in a different color here. We have magnesium, we have strontium. And so which one is larger? Well, the strontium is larger because it's farther down within the same group. Okay, same reason that sodium is larger than lithium because it's in the same group. Next one is carbon or germanium here. Okay, so carbon or germanium. Okay, and which one is larger? Well, germanium is farther down within the same group, so it's going to be larger as well. So that's germanium. All right, fantastic. Now we got that. So the next one is selenium or calcium. Okay, so selenium, and let's see here. That is right over here. And we'll do this here and then hash it a little bit. Or the calcium, and then we'll do that one here and then hash it there a little bit. So which one, again, is the larger of the two? And so as you go to the right, they get smaller. Selenium is smaller than calcium within the same period, or as you're doing my arrow here on the bottom, as you go to the left, they get larger. So what's larger? Calcium is larger. So I'm going to circle that calcium right there like that. Then the next one is nitrogen or arsenic. Okay, and so we have nitrogen or arsenic. And again, the further you, this is within the same group, the farther you go down within the group, then of course the larger it is. So of course that would be the arsenic would be larger. And then our next one, our last one on this subset here is boron or fluorine. And boron or fluorine. So we have, let's see here, boron and hash that, and fluorine, and we'll hash that. And again, the textbook reason, the textbook one is that as you go to the right, they get smaller. So fluorine is smaller. The question is which one is larger? So that would be boron would be larger. So I will do that right here. So there we go. Hopefully you should see all the answers right here on this sheet of paper, but truly what we are doing is we are looking at periodic trends to find the answers to these questions here. Hopefully that works for you. Yep. Okay. Fantastic. So now what we're going to do is we're going to flip to a new periodic table because we're going to actually do a new trend for a new question. So going for this one here, and this is going to be question number 14 because that comes after 13, of course, and which has the greater first ionization energy? So ionization energy. All right, so ionization energy. So really, we're going to be looking at these questions here, number 14. And let's see if I'll zoom in right on that so that you can see these here. And it says, which element in each pair has the greater first ionization energy based on periodic trends? And so we have A, B, C, D, and E here for this. So we're going to see what we can do with this set. So we're first going to figure out ionization energy and what is the trend for ionization energy. So zooming on out so we can see our periodic table. And ionization energy is opposite of size. That's the beautiful thing. So if you remember that size is large down here at the francium area, is very large in size. That is, it gets larger in size as you go down the group, gets smaller in size as you go to the right. That means it gets larger as you go to the left. So ionization energy, that is the ionization energy is the removal of electrons. So if you remember back on the first video, it's problem number 6, what is meant by the term ionization energy. So you have to go back to that. It's the removal of an electron from the gaseous state. Okay, so that means that this element right here, fluorine, would have the greatest ionization energy since it's opposite of size. So ionization energy follows the following trend. Gets larger as you go to the right and larger as you go up. So this is large. Large in terms of ionization energy. Okay, so let's see if we can answer these questions based on this information here. Okay, all right, so the first one was lithium or boron. And so what we're going to do is we're going to circle lithium and boron, and which one has the greater ionization energy? Well, the one that is further to the right. And so that would most certainly be boron. So let's circle that one. And again, this is larger, greater first ionization energy, larger ionization energy. So that's boron because it's further to the right within the same period. Okay, the next one is going to be magnesium, or strontium, magnesium or strontium. Okay, and so we're looking for which one has the greater first ionization energy. And since ionization energy increases as you go to the right and increases as you go up within the group, we're looking for the greater ionization energy, and that would be magnesium because magnesium and strontium are in the same group. So that is magnesium, most certainly. Okay. The next question is cesium or aluminum. Cesium is right down over here. Aluminum is way up over here. And which one has the greater first ionization energy? So now we're not talking about in the same period or within the same group, but we are talking about the generic trend for ionization energy is that as it goes to the right and up, it increases in ionization energy. So that means that the further you are to the right, the further you are up within the same group, further you are to the right within the same period, you have the greater ionization energy. And aluminum is both to the right and further up than cesium. So most certainly, aluminum will have the greater first ionization energy. All right, the next one is going to be boron or fluorine. And so let's see, we'll have to do another color here. So we'll do boron and fluorine. And hopefully you can see that boron and fluorine are within the same period. Fluorine is farther to the right, so therefore it will have a greater first ionization energy. So what we're going to do is highlight that fluorine. It's going to have greater first ionization energy. The next one is going to be nitrogen or arsenic. So we've got nitrogen or we've got arsenic. So the greater first ionization energy is the one that they're in the same group. So the one that is further up within the same group, higher up in the group, that's nitrogen. So nitrogen for this within the same group. All right. Fantastic. Hopefully that works out well for you, and make sure that you got that. Quick little advertisement. This video is sponsored and brought to you by the Crazy Hat Chemist. And who is that? Well, that's me. I'm the one speaking here. So I'm the one that made up this stuff, or at least the worksheets, and I'm the one here hoping to teach you some chemistry. So this is what we have for this problem right here. You can see the ionization energies here on this chart here, and hopefully that works for you. All right, so now what we're going to do is we are going to go on to question number 15. All right, so let's flip this periodic table off to the side. We're going to cruise on over to number 15. We're going to zoom in on that because we need to. All right, here we go. And there we go. So number 15, it says, why is there a large increase between the first and second ionization energies of the alkali metals? Okay, so we're going to get an answer to that. So I want you to just take a moment of pause and look at that and see what you can come up with as far as a concept on that one. Okay, so let's see, the alkali metals. So the first thing that we need to do is figure out where are the alkali metals. So the alkali metals is right here. This is group 1. So the alkali metals are group 1. So I'm going to ask you, since it's in group 1 for the alkali metals, how many valence electrons in group 1? That's correct. That's one valence electron in the alkali metals. And that's a very important concept here. Okay, so generically, ionization energy increases as you go up the group. So that means that lithium's ionization energy is the highest of the alkali metals, then followed by sodium is the second highest, then potassium, rubidium, cesium, and then of course francium, they're off the chart. Okay. But what we're really looking to do is answer this question here. Why is there a large increase between the first and second ionization energies of the alkali metals? Okay, and so in order to answer this, we're going to write out a little bit of a long response here so that you can fully understand what is going on. Okay, so the alkali metals only have one valence electron. So let's see if we can write that down. Alkali metals have one valence electron. And by the way, these are valence electrons, not valence electrons. A valence is something that goes above your curtains or something like that, right? Okay, so these are valence electrons, not valence. All right, just to clarify that little tiny small point. Okay, and so the first ionization energy is the removal of that first electron. But once this valence electron has been removed, so hopefully everybody understands the alkali metals, since they're in group 1, have one valence electron. Okay, but once that valence electron has been removed, then what type of electrons remain? Those are remaining electrons are core electrons. Okay, after you remove the first electron, which is the first ionization energy, okay, the core electrons are what remain. And core electrons are very difficult to remove. Okay, so remaining electrons are core. And these electrons are difficult to remove. For one, they are closer to the nucleus. And two, the effective nuclear charge has increased. Because you have removed an electron, the effective nuclear charge has increased. So the second ionization energy is much, much larger than the first for the alkali metals, for the reasons that you have removed the valence electron, the remaining core electrons are closer to the nucleus, and the effective nuclear charge has increased dramatically. Okay? Okay. Hopefully we got that. Let's see if we can handle the next question. That's number 15. Now let's go to number 16. Why is there a large increase between the second and third ionization energies of the alkali earth metals? So we're going to go back to our periodic table and figure out what are the alkaline earth metals. So the alkaline earth metals is group number 2. Okay, so group number 2, alkaline earth metals. Okay, so the question is, why is there a large increase between the second and third ionization energies of the alkaline earth metals? So I'm going to try something different here on this one because it's really the same answer as number 15, but just a fine minutia point. Okay, and I'm hoping that you remember writing out electron configuration. So of electron configurations, we're going to do the noble gas electron configuration for magnesium. So for magnesium, which is element number 12, noble gas prior to magnesium is neon. So neon, and then it is a 3s2. Okay. If I were to write this out fully, it would be 1s2, 2s2, 2p6, and then 3s2. Okay. So where are the valence electrons? How many valence electrons are there? It's the largest principal quantum number. That's a 3 in this case, s and p, and there's only 3 and s's. So how many valence electrons in magnesium? 2. How many valence electrons in magnesium? Largest principal quantum number, s and p, 2. And you can get that from the periodic table as well. How many valence electrons in group 2? 2. Okay, so removal of these 2 valence electrons, now what type of electrons remain are core electrons. What type of electrons remain are core electrons. So there is the first ionization energy for anything in group 2. The first ionization energy is relatively low. And the second ionization energy is higher than the first, but still relatively low. And once you have removed those 2 outermost valence electrons, then what remain are core electrons, and core electrons are exceedingly difficult. So that third ionization energy would have to be one of these core electrons, and that is almost an impossible feat. So that's why there is a large increase in ionization energy for the third ionization energy of group 2. Okay, so hopefully you understand that. All right, so let's go on to our next one here. So number 17, it says, which of each pair has the larger radius atomic size in each pair based on periodic trends? So we're talking about size here again. So we're going to go back to our periodic table that we had before. We're going to rewrite this one so it looks good and pretty. So we're going to pull this away and we're going to pull out our periodic table. I'm going to zoom on out so that you can see the whole thing here on this. All right. So in general, size. So size, which would be atomic radius. So atomic radius, size, one and the same term thing here, effectively. Okay, and so for this first one, what we're looking at here for this first one is between sodium or sodium ion. So all these are between the ion and the element itself. So that's what we're looking at. So sodium and sodium ion. So really what we are looking at is trying to do an electron configuration, and hopefully that will make sense for you on this. Okay, so what we're going to do is an electron configuration for sodium. So I'm going to do the full electron configuration for sodium, and then we'll do the full electron configuration for the sodium ion. Okay, all right, so the full electron configuration for sodium is 1s2, that's 1s12, 2s2, that's 2s2, and then 2p6, 2p6, and then it's 3s1, 3s1. Okay, so there is the sodium element that has a charge of 0. Okay, that's why that's like that. And then we're going to do the sodium ion. So the sodium ion, notice it has a 1+ charge. So if you have a 1+ charge from something that has a 0 charge, you're going to have to remove an electron. That gives you now more positive protons in the nucleus. Okay, so I'm going to remove the valence electron. There's only one, so it's 1s2, 2s2, 2p6, and then I'm going to just write this in black here, and that's 3s0, 3s0, right? You don't actually have to write this. Many people don't, but I'm just writing that down so that you can see that this 3s1 electron has been removed. That's why it's 0 here. So which one is larger in terms of size in regards to this? This is going to be a generic trend here, and that is metals lose electrons. Sodium is a metal, so metals lose electrons, okay? And metals are always larger. The metals are larger than their ions. Okay, and the reason for this is that the ion has lost a shell. It has lost the 3s shell. And furthermore, the effective nuclear charge has increased. So the nuclear charge itself has not changed. That is, sodium atom element has 11 protons. Sodium ion has 11 protons. But the keyword is effective nuclear charge has increased. So the metals, of which sodium is a metal, are always larger than their ions because the ion has lost a shell. That's the 3s shell. That shell is now open and empty, vacated. And the effective nuclear charge has increased. That means that there are fewer electrons here. So that's why the effective nuclear charge has increased on this and draws these electrons that remain. That is, 10 electrons are here and 11 electrons are here. These 10 electrons are drawn tighter in. And so the larger is the sodium atom. All right, perfect. Let's go ahead and circle that right over here. And then the next one is iodine or the iodide ion. So what we're going to do is we're going to draw that out and so that you can see that. So slide this over just a bit. And where is iodine? Iodine is right over down here. And so what we're going to do is we're going to draw out the electron configuration for iodine. We're going to use the noble gas notation. There is iodine, so that would be krypton. So iodine, and this is element 53, and then that has no charge, and the iodide ion, and that's still element number 53. Okay, so we're going to use the noble gas notation here for convenience sake. So that's Kr, that's krypton. And after krypton, hopefully you recognize the periods on the left-hand side there that I just labeled. So krypton and then 5s2. So that's 5s2. And then 4d10, 4d10. And then 5p5, 5p5. Okay, that is for the iodine atom. Okay, and then for the iodine ion, what has happened with that one is that you have added one electron. So that's why it has a -1 charge. So we're going to do 5s2, 4d10, and 5p. And then I'm going to write this in blue, 6. So there's one more electron with the iodide ion. So which one is larger in terms of size? And that would be right over here. There we go. Which one is larger in terms of size? That is right here, larger. Okay, and so this is also going to be a trend. And with nonmetals, the ion is always larger. Why? Because the effective nuclear charge has decreased, okay? And that effective nuclear charge has decreased because you've added an electron. And so you cannot hold on to the 54 electrons in this particular case, with those 53 protons in the nucleus. And the electron-electron repulsion in that outer shell, because you've added another electron here, has increased the size as well. So hopefully you understand this, that there's a big difference between metals and nonmetals. Okay, and with metals, sodium being an example of that, metals, the atom is always larger than the atom because the effective nuclear charge has increased with this ion and you've lost a shell. Conversely, nonmetals, the effective nuclear charge has decreased with the addition of an electron, and the electron-electron repulsion in that outermost shell has increased. So therefore, you should see this trend, and that is the ion for nonmetals is larger than the atom, and the trend for metals is that the atom is larger than the ion. Okay, so hopefully that is going to answer the remaining bit of these questions here on all of these. And so let's see if we can hammer these out. So we just answered A and B. So then we're going to go to C. We have sulfur or sulfide ion. Which one is larger? Well, this is a non-metal because it has a negative charge. So the ion is larger than the atom. Then aluminum and aluminum ion. Aluminum is a metal, so which one is larger? The aluminum atom is larger. Titanium or titanium ion, of course, this is a metal and the atom is larger. Again, this is a cation. Phosphorus or phosphide ion. Well, this is a nonmetal. So what is larger? The ion is larger. Okay, now we are going to do, so we've answered these based on either a metal or non-metal, and then we can go from that. The next one is potassium and chloride ion. So what we really need to do is go back to our periodic table here and figure out which one is larger based on size. So if you have elements that have their periodic trend charges. And so I'm going to highlight, we have what, potassium ion here, and then the chloride ion over here. Okay, and so the potassium ion is a 1+, the chloride ion is a 1-. And so the trend in size is that you should see that this follows the basic trend size, okay? And these are actually, these two are going to be very, very special because potassium, when it loses an electron, it will have now 18 electrons, but it has 19 protons. So it's going to draw in those electrons because there are fewer electrons than protons, so it's going to get smaller. Chloride ion is going to gain an electron, so it's going to have 18 electrons. So notice the potassium ion and the chloride ion have the same number of electrons. This is called isoelectric. So iso means the same and electric means charge. So these two are going to be isoelectric of each other. Okay, so the potassium ion and the chloride ion are isoelectric. So the chloride ion is going to gain an electron and its effective nuclear charge is going to decrease. So it's going to get bigger. Whereas the potassium ion is going to lose an electron and its effective nuclear charge is going to increase and it's going to get smaller. So which one is going to be larger? Well, that would be the chloride ion. Okay, and so the chloride ion is going to be larger than the potassium ion because they are what are called isoelectric. So that's a very important concept here. All right, our next category here, our next one is phosphide and sulfide. So phosphide is right here. This has a 3- charge, and then sulfide here, and that has a 2- charge. And we're looking to figure out which is larger in terms of size. Okay, so which is larger in terms of size. So if they are the periodic trend of their ions, of which these are, this is a 0, a -1, a -2, -3, and they are all nonmetals, then it follows the trend in size. And that trend in size is as you go to the left, they get bigger. So the phosphide ion is biggest of these two. In fact, the phosphide is larger than sulfide, and sulfide is larger than chloride. Good. Okay. Hopefully you got that. So that is question number 17. All right. All right. So let's move on to our next problem, which is problem number 18. So problem number 18, let's see if we can fix that up here for you and zoom on in. Problem number 18, it says the following. Which of each pair has the larger or higher electronegativity value of each pair based on periodic trends? Okay, so again, periodic, I have not actually said this, but I do want to say this. Periodic trends are just trends, right? Like trends of many things, right? Like what is the trendy thing right now is, you know, have jeans with holes in it. In just the next week, then jeans with holes in it isn't going to be cool anymore. And so no one will wear jeans with holes in them anymore. What's cool is wearing Vans shoes. And then eventually Vans shoes won't be cool anymore. And it will be K-Swiss or some other, maybe it's Nike shoes will be cool then at that point in time. But whatever is cool, those are the trends. But does everybody wear Vans shoes? No. Does everybody wear K-Swiss shoes? No. Does everybody have holes in their jeans? No. So not everyone follows the trends, just so that you know. These are trends. These are not based on absolute numbers. They are based on some numbers to start off with, okay? But they are just trends. All right, so let's see if we can answer number 18. Which of each pair has the higher electronegativity value in each pair based on periodic trends? Chlorine, fluorine. And so what we're going to do is we're going to pull out a periodic table and we're going to answer that using our periodic table, of course. Zooming on out just a little bit more here so that we can do this. Here we go. How do you like my new weight? Crazy Hat Chemist. I etched that in there. And then I got an additional new weight too. Got a gold and silver one. Well, it's not real gold. Maybe one of you will buy me a real gold weight and sketch in Crazy Hat Chemist, or maybe buy me a whole full silver one. But that will tarnish too quickly, so that wouldn't be any good. All right, so which has a higher electronegativity? So first of all, electronegativity. Okay, electronegativity is generally viewed as a scripted X. Where is the highest electronegativity? That would be right here with fluorine. Fluorine has the largest electronegativity value. And being that this is the largest, then that means that the trend is going to the right, has the larger value, and coming up within the same period. Coming up within the same group has the larger electronegativity value. So as you go to the right within a period, it gets larger. As you go up a group, it gets larger in electronegativity value. So let's see if we can answer that. Okay, so now that we got that trend in electronegativity, now what we can do is go back to our questions and see if we can answer this. So our first question is, let's see, I'm going to fold this over here just a little bit so that you can see that. Perfect. All right. So chlorine or fluorine? So chlorine or fluorine? Which one has the larger electronegativity value? Well, fluorine is top dog in electronegativity, so it is most certainly fluorine. There's no doubt about that. Next one is carbon or nitrogen. Okay, nitrogen. There's nitrogen, there's carbon. Which one has a greater electronegativity value? Well, they're in the same period. The one further to the right, that would be nitrogen, would have the greater electronegativity value. All right, the next one is magnesium or neon. Magnesium is right here, and neon is right here. So here is a funny thing. The noble gases, their electronegativity values are very, 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 very low relative to everybody else. Even though, let's say, neon is extremely close to fluorine, the noble gases really have electronegativity values that are very low. So magnesium is going to be higher just because it's a metal, and that's just the way it is. So we're going to circle the magnesium. Okay, next one is arsenic or calcium. And let's see, we have arsenic and we have calcium, just like that. And arsenic and calcium are within the same period. So as you go to the right, then the electronegativity value increases, so that therefore the arsenic would have the greater electronegativity value. Then we have boron or fluorine. So boron or fluorine, and this is hopefully a duh. Fluorine is the greatest in electronegativity, period, bar none. So the fluorine, that's just a duh. Then we have nitrogen or arsenic. And so we have nitrogen or arsenic. Okay, and the trend is as you go up within a same group, then the increases in electronegativity. So that, of course, would be the nitrogen. And so that is the nitrogen has the greater electronegativity value. All right. So hopefully those worked out well for you. All right, I'm going to stop here and we are going to end with this problem number 18. And next time we are going to continue with problem number 19. So that's where we're going to start for the next video. This will be part 2 of our series and we'll have more to continue on for next time. So I hope that you have a fantastic day. I would greatly appreciate you giving me a thumbs up and subscribing, and please give me some comments. I'll answer those comments. I'll talk to you next time. Love y'all.